Okay, so we're looking at page 5 of exam 2 in the spring semester of the second semester of organic chemistry. And we're asked to propose some mechanisms for the following transformations here. So let's take a look at what we can figure out. So up here, move that out of the way here a bit, we have two phenols, we've got some acetone, we've got some HCl, and we're supposed to bring them together to make this behemoth over here, right? So let's start to think about this a little bit, try to piece things together, how we can get from one bit to the other. Now, it'd probably be a safe assumption to say that these OHs are those OHs there, right? We're not explicitly told that there's any water around, so it's, under these conditions, it's going to be very unlikely that we can, end up swapping one OH for the other. What would be the point in doing that? We say, okay, well, that kind of makes sense, but what's the point in that? Well, the point is that, right, then we know that we're going to have to add something to the para position of those phenols there, right? And say, oh, okay, so we're adding something to an aromatic ring that's a, electrophilic aromatic substitution, right? These are activated rings. This is not going to be a nucleophilic aromatic substitution, right? This is going to be electrophilic aromatic substitution. Sorry about that. I'm still kind of getting over this cold here, so I don't want to cough into the microphone here. But just to pick back up here, right? We have activated aromatic rings with those OH groups. We're adding things to a para position, right? So we're going to have to go through electrophilic aromatic substitution, right? That's a great place to start. You say, okay, well, if I want to go through electrophilic aromatic substitution, I have to generate a good electrophile. Now, HCl itself is not a great, it is, a proton is, an electrophile, but we're going to need to kind of make a better electrophile to make this go, right? This is one of the discussions that we had with regards to the mechanism of electrophilic aromatic substitution. Okay. All right, so we got all that down. We want to do electrophilic aromatic substitution. We have an acid. We know that we have an acid. Typically, they're going to do acid-base chemistry first, right? That's usually the fastest reactions to happen. And we've got a ketone around, right? Okay, so ketone with acid. There we go. We're going to grab that acid, we make a bond, we break a bond. So, all right, well, what's the point in that? Well, indeed, what is the point in that? So here's what we did, right? Well, we don't really need those electrons there. You guys know at this point about formal charges and all that. Okay, so we made that. Say, great, who cares, right? Well, it's important because we can do this, right? We can draw a resonance structure, right? We can draw a resonance structure to indicate that we can have a very activated, right? We can have a carbocation of sort, right? A resonance stabilized carbocation, but still a carbocation. That's a pretty good electrophile. Not a great one, right? It's not a full carbocation, right? It's a resonance stabilized one, but it's a pretty good electrophile. Now, why am I making this distinction? Well, if you go back and you rewind a little bit, you'll notice that I discussed briefly that phenols are activated, activated aromatic compounds. And remember, we talked about activation, and we kind of directly tied this to ortho-para directing versus meta-directing, but it's not interchangeable to say that just because you're an activator, you're ortho-para directing. Like they are, but I want to draw an important distinction about what it means to be an activator versus an ortho-para director, right? Activating means that the aromatic ring is more reactive towards substitution, right? It's easier to get the aromatic ring to react, right? Hopefully that kind of makes sense, right? I don't know how else to really describe this, right? If you're activating something, right, you're activating it towards acting, right? So what that means is we don't have to have as good of an electrophile with an activated ring, right? Phenols, in fact, I believe with bromination, they just kind of brominate under standard conditions, right? We don't need anything too harsh to get this to work. But, activated rings is all. What I'm really trying to say is activated rings react. What a profound statement. All right. So anyway, let's take one of these activated rings and let's act. All right, so let's bring it in. Red seems reasonable. Okay. So send in a pi bond to hit that resonance stabilized carbonyl. Now, you can hit either one of these compounds. You can either hit one or two. Remember, structure one is going to be the more dominant resonance structure in equilibrium. So we could have just as easily done this, right? Hit that and then hit that. We could have drawn those two arrows. Either one is fine. Like I said, we're just doing a mechanism in this case. We're not sending something to Mars here, right? So here it is. Well, let's say we made that bond there. We hit a carbon that had those two methyl groups and our OH on it, right? And our consequences of our actions are we generated a carbocation on our aromatic ring. We could go through and draw all the resonance, right? We could go through, draw resonance stabilization of that positive charge there, right? That'd be a good practice for you guys. But anyway, right? Part of electrophilic aromatic substitution is one of the pi bonds reaches out, grabs an electrophile, and then we have to reform the ring. Let me zoom in here for just a second so I'll show you what the shenanigans that we're about to do here. Okay, so we have to accomplish two things, right? One, we have to reform aromatic ring, right? We broke an aromatic ring. There's a strong drive to reform it, right? And two, generate another nucleophile. Excuse me, generate another electrophile, right? We have to generate another positive charge. And we have to do these two things. You say, okay, well, why? Well, remember, right, to reform the aromatic ring, right, aromatic rings are stabilizing. There's a strong drive thermodynamically to reform aromatic rings, right? To generate another positive charge, well, we have to add another phenol, right? And to add another phenol, we have to go through another electrophilic aromatic substitution. And to do another electrophilic aromatic substitution, we have to generate another positive charge. That makes sense? So we have to reform our ring. We have to generate another positive. All right, so we're going to do this at the same time. Let me just slightly draw this here to make it a little bit easier to see what we're about to do. So to reform the aromatic ring, right, we're going to have to get rid of this hydrogen and take our electrons there to reform a pi bond. So something's going to have to come in and pluck that hydrogen off. So let's do that, and let's do that, okay? You guys catch that? So let's draw what I just did. Okay, there's my O, there's my H. Let's see, I used blue to grab Mr. Purple to make blue pi bond there. Okay. All right, you guys catch what I did there? Something had to come in to grab that hydrogens, right? Hydrogens aren't just going to leave on their own, right? Off the top of my head, I can't think of a mechanism where an H plus just leaves, right? Although I'm sure there's some organic chemist screaming at this video, and they know exactly. Like, yeah, there's the blah blah blah, elimination. No, okay, sorry, I don't know about it. Don't know everything, right? But anyway, so something has to happen for a reason, as I guess a good place to start, right? So something's going to come in and grab that hydrogen. We've got an OH that's around, so it's logical that that OH would internally grab that hydrogen there. Does that necessarily mean that that's always going to happen that way? No. Does it really matter? No, right? At the end of the day, though, we have to protonate that oxygen to generate another positive charge, right? We have to make a good leaving group to generate another positive. right? We have to accomplish that right here. Okay, so let's do that. We made water. Let's make it leave. Whoops, I almost didn't listen to myself. Okay. You say, hey, wait a minute. Why did that happen? Why couldn't I just, let me pause here for a second, take a teaching moment. Let's bring this down here. Why couldn't I just do this? Why couldn't I, at this point, just do this, right? Well, can you guys think of a reason why that might be? Right? What are we somewhat showing in this mechanism here, right? Well, we're showing an incoming nucleophile, right, hitting a tertiary carbon, right, and popping off a leaving group, right? Well, this is, not really, this is sterically forbidden, right? Uh, Although I got to put heavy air quotes around all this, right? We can't do this type of attack on a tertiary carbon, right? This is kind of one of those things that we talked about in SN2 reactions, right? So we got to talk about sterics and incoming groups right there, right? So we're not really going to end up doing this here, right? But a good idea, right? Terrible, it's not a terrible thought, right? It's just we have to kind of clean some of this up, right? In essence, we are going to accomplish this. It's just we have to do it in 2 steps rather than 1. Got it? All right. So we generated our carbocation up here. It's a nice stable carbocation. It's tertiary. It's benzylic, right? Hard to get more stable than that, right? All right. So let's bring in our next phenol then. We used red last time, I think, so let's use red again. Now we can hit that there, right? And we'll just pick it up from down here, right? And we'll draw a line to know that we're just picking it up. Okay, so there's this. Boom, boom. Give me a minute here just to draw everything back in. All right, so we did red here. We've got Mr. Blue pi bond there. We've got black carbon, and then we connected that right there. Okay. We have positive charge. We've got Mr. Purple hydrogen there again. So you guys can probably see what's going to happen next, right? Another acetone molecule could come in. Maybe a phenol could come in, right? Phenols aren't that basic, right? They're really not that basic at all. The conjugate base of HCl could come in, right? Some of the water that we kicked off up here could come, right? So something's going to come in. And so we're going to abbreviate that something with our good old buddy base, right? Some base is going to come in, grab hydrogen, and we'll do this in black, right? And slam down the pi bond to reform our aromatic ring. Got it? So something's going to come in to grab that hydrogen. We don't really know what, we don't really care what, because it's not part of what we're interested in at the moment, right? And at the end of the day, what did we make after all of our shenanigans? Don't worry, I'm coming back in with color here. So we made this guy, right, and this guy here. Okay, cool, great. Behold, a mechanism. All right. Not too bad, right? So I'm going to pause here just to, I don't want each video to end up being like 30 minutes. So there's the first mechanism. We'll pick up the second one in the next mechanism. in the next video, I mean.